we're joined by Professor Maria, Professor of Economics at the University of Santiago de Compostela. Professor Maria's research combines climate science, economics, and data analytics to inform risk assessment and policy design. She has published widely in leading journals, serves as editor of Ecological Economics, co-editor of Environmental and Resource Economics, and has been recognized among the top 2% of most influential scientists worldwide. A previous attendee and presenter at the symposium, Professor Maria's today talk to us about AI-driven damage functions, rethinking climate impacts for policy and risk assessment. She will introduce AI-driven damage functions, new approaches that leverage advances in climate science, economics, and machine learning to better represent risks and associated economic impacts related to climate. Please join me in welcoming Professor Maria.
Well, good afternoon. Thank you very much. It's a pleasure to be here. Your Excellence, thank you so much for your time. It's an honor to be here, actually, and thank you all for attending. And I'm very happy to be here, for sure. So let me tell you, I don't want to take too much time, but we have 20 minutes, so that we don't go over the time limit. I would like to tell you a little bit about damage functions and how we are thinking about climate change right now into macroeconomic modeling, and why has happened in the past that, as it turns out, although climate change is for sure one of the largest or the largest concern that as a humanity we are facing, still percentages of GDP losses associated with climate change are computed as very small. 2%, for instance, of GDP loss in 50 years, and so on, are recent estimates generated by DICE 2023 models, which have been generated also by Nobel Prize winners. So why is that? Why being climate change such an extreme event, such a drastic problem for humanity, why macroeconomic modelers still are presenting relatively small GDP losses? Well, this is what I'm trying to respond in this talk, and I'm trying to facilitate other results that hopefully shed light with respect to actual and future losses. And in order to do that, I'm going to be extending an integrated assessment model that I'm going to be computing with an algorithm generated by Gazotti, and which is a much more disaggregated level than previously estimated. It's a high-resolution model with 57 regions. So I am really a firm believer that AI is going to be very helpful in order to address climate problems and hopefully to help us to design better climate policies. What I'm going to be talking about basically is how we should be approximating these important climate damages, and in particular focusing on the damage function. When we estimate macro models, we need to face how we are going to be estimating this relationship between climate and GDP. Usually in the past it has been estimated with respect to growth in temperatures or increase in temperatures with respect to losses in GDP, associated losses. And the initial models we estimated were relatively simple. They were basically thinking on a linear relationship. 1 degree more of temperature will lose, for instance, X% more on GDP. But very, very simple models. Later on, we included a more sophisticated approach in which, we thought about hazards being nonlinear, which is great, and this is fantastic. But more recently, we're also thinking, these hazard functions, these damage functions may not be even continuous. There may be some thresholds in which there's a huge jump, unexpected jumps, and so on and so forth. It is rather complex to estimate a good damage function, and that I can assure you, because there are multiple issues that have to go into detail. For instance, we are looking at any natural loss. We also have to be considering also anthropogenic forces. We have to be considering public policies in force, and so on and so forth. So it's rather complex, but still many things can be done. I'm sure that many of you have listened to many traditional concerns with respect to the functional form that I'm going to be talking about. The discount rate that someone was asking about, what discount rate should we be using, or how do you estimate your optimal discount rate? But there are also current concerns that are very relevant with respect to omitted variables specifically, and new estimation techniques, or all estimation techniques that have been employed that may have generated certain results which are not ideal or not optimal. Let me first highlight some relevant results with respect to the functional forms. First of all, Nordhaus, also a Nobel Prize winner, suggested that for sure we should be considering quadratic forms for the damage function, in which the damage function has been represented like a percentage loss of the GDP. And they were only considering temperatures. Temperature and temperature square were the basic approximations of how GDP loss was modeled, only with respect to temperature. Certainly, temperature is part of the deal, but not all. Extreme events could be very crucial as well, and they are not included there. So there are certain specification bias that new climate economics is addressing. In spite of all this pioneer work and following the work that had been focused previously, as you may have seen, by Nordhaus, that focused on increase over average temperature and its square, other approximations have looked at the streams. Okay, let's look more at the stream. What happens if the temperature is going really up, high up? And that will be the approximation more of the Weismann model, looking at the streams, but still only facing the variable temperature. Other issues that we should be considering, well, the discount rate. We are looking into impacts on our economy that may take an effect now, and it will be extended through multiple generations. Or even though, as Stephen Chu was saying, we are emitting now, for instance, nitrates, CO2, and some of it may be alive in the atmosphere for 100 years. So what are the expectations for future generations? What is the future in terms of well-being and economic performance? And how we value the future is, of course, part of it, and what discount rates are we going to be using to bring up all these future positive effects into current units, or future damages into current units. How do we do this cost-benefit analysis, and which discount rate are we going to be using? At the beginning, there were not that many recommendations, but nowadays, luckily, there are many recommendations for very reputable agencies. At the moment, for instance, we have seen that the US Office of Management and Budget has suggested about a 3% nominal discount rate per year, but this, of course, is matter of huge debate. In the UK, they employ something else, and the European Union, they are recommending around 2.5%. So these are some ideas that we should be considering. So now we have basically all components. We have spoken about the discount rate, our epsilon there. We have, our rho there. We have also talked about the damage function, so we are ready to understand what is the impact in terms of social cost of carbon, understanding social cost of carbon as the value, the present value of all future damages caused by 1 ton of CO2 in a particular economy. As you have may expected, given that there are multiple models around the world, there are multiple estimates. That's not a surprise. And some estimates go between a very conservative, around $40 per ton of CO2 right now, up to 150 or more. But so, as a researcher, I was wondering why this variation, how we can understand this, and what will be expected under different conditions. So what I have done, although there's a lot of math, I'm not going to go into it, was to replicate this model that is more, much more detailed in terms of these 57 regions that have followed previous integrated assessment models. And we have tested how the performance of the different damage functions will affect the estimates. So we have revised the literature, we collected the most relevant damage functions that have been published, and we ran the same model utilizing different damage functions. In order to understand what? In order to understand well, what are the differences in the outcomes and final estimates over GDP? So, and this is one of the first estimates we are providing, the calculated impact, or basically, well, what is it telling us in terms of performance of integrated assessment models and how much it costs right now? What is the effect of 1 ton of CO2 in the economy? Well, and here I have in the model, we have 57 regions. All, and in particular regions at times can be differentiated across countries. For instance, I have Spain, my region, my country, and I have UAE also here, and US, for instance, as a comparison. So what do we learn? Well, the social cost of carbon right now is much lower in this part of the world than in the rest, and it makes sense. Why? Because of higher income in the region. Of course, higher income allows to have better climate technologies at the moment. But with the time, when after 50 years, or when we look at 2050, for instance, we see that there's a huge jump in the social cost of carbon worldwide. So the question before is like, how long do we have? Well, it depends on what do we want to achieve, how do we want to achieve. But apparently, before 2040, there is a huge jump in the social cost of carbon worldwide. So we have a limited window for dealing with the climate impact worldwide. Of course, these effects that we are seeing here are magnified when we pass over 2060. So when we predict a long, very, very long term, certainly these are huge numbers, and I'm not going to go into detail, but you will see that if we don't correct, or we are not able to correct the climate crisis right now, then afterwards it's going to be economically unbearable. These results are usually replicated with different formulations. No matter what damage function specification you employ, even you can employ the very traditional specification as before I have shown you with a temperature and temperature square, that you still will find a similar perspective of the results. So results are replicated, results are fairly robust for the at least first 50 years. It changes slightly, but they are fairly robust. Once again, they always suggest, integrated assessment models suggest that, well, we should be a bit rushy in the terms of adaptation to climate change because it's going to be very complex. And I could tell you about many more specifications, but there is no time for that. But still, what I wanted to say is that there is a robustness in the data that is clearly observable, right? So we have seen that the social cost of carbon is increased significantly over time, and they become more homogeneous. They are heterogeneous at the beginning, but they become more and more homogeneous. And of course, it's very important to consider that we are using, the more disaggregated data we have, the more heterogeneity we understand, right? And the more able we are model to model heterogeneity. But there is a big but still. And the big but is the fact that extreme events each time play a more crucial role in understanding climate and climate impacts. And this has to be also included into the damage function. And some of it we have already included, but still there is much more to come. If you observe, for instance, this is the United States $1 billion disaster event, in which, as the name indicates, only disasters which overpass $1 billion are registered, but they are growing exponentially. And this happens worldwide. So we have to be considering that, well, climate change measured by temperatures, temperature square, cubic temperature, so on and so forth, is still a very naive approximation. We have to consider extreme events. And particularly health impacts. Health is crucial. And this is an example of how many people has died in Spain, my country, in the last year with respect to climate change. 6,100 people have died in Spain. You see, they have died because of deficit of temperatures in January, February. It was very cold, Sundays, and also during the summer. time. So, and this has been a huge amount of deaths. The death toll is increasing in Europe, and in the last year in total, about 60,000 people in Europe die with respect to climate change. So my work now is including these aspects that I mentioned, modeling extreme events, and also including health, into a higher resolution model that we are running, as I am speaking, based on artificial intelligence algorithms. And I am very confident that hopefully we will be able to overpass some of the limitations. For instance, in the past, temperature and temperature square are highly correlated. So the problem is that the coefficients are not good estimates for sure, and maybe they should not be included into macro models to start with. Furthermore, nonlinearities. Nonlinearities are rather complex, and AI allows us to include, or is able to generate better estimates under these conditions. In one of the pieces of work I have with some colleagues from here, we have observed that the correlation between temperature and yield for an agricultural product is practically zero, the linear correlation. And therefore, many nonlinearities are very persistent. Also missing values that help us with that, and the granularity of data. So in fact, hopefully, we are expecting that we are going to be generating much better estimates thanks to AI applications. So these are some of the components that I will be including. So mortality impacts, extreme events, and other social spillovers related to extreme events. And hopefully with that, we will have a better representation. We are going to try to do that with very microdata, because we believe that microdata is the future, and hopefully we will be able to replicate something as this one. This is a work that we have undertaken with some colleagues who may be here, and they are from Khalifa University, some of them, and we look at the importance of climate change in an agricultural commodity in Spain, in wheat, right? And that was very interesting to use this microdata, because we tried to collect all the historical data that we could, more than 50 years of data, to understand the difference between weather and climate, of course, and try to model the closest possible the impact of climate change. And it was very interesting to see that when we tried to use this data from the meteorological stations, as you see, it's very granulated data. And of course, we collected temperatures. We collected a lot of data with respect to droughts, extreme events, as I was mentioning, droughts, heavy precipitations, winds, and also, of course, labor and fertilizer. Also, Stephen Chu made a very good point, the fact that how we are adapting to climate change, for instance, in the agricultural sector, is to use more fertilizer to try to compensate, right? And because of that, we are generating a huge problem with nitrogen. This is using our estimates show very interesting results in terms of heterogeneity, in terms of how some regions are going to be losing production with respect to others. And we have generated 3 clusters. The green, those are the regions those are the provinces that will lose less. The blue, which is the intermediate, and the red, which is going to be heavy losses of agricultural yields, which are going to be present in that. But in general, the use of these microdata show us that reductions of yield are well above than those previously recorded. And why is that? Because microdata is very rich. And having richer data, you are able to approximate much better the damage function. Another things that we are doing in terms of understanding the spillover effects of climate is with respect to extreme events that occur and that are described in social media. And there are fundamental issues there with respect to misinformation, which is a crucial problem that we are facing with respect to climate change. these are some of the most relevant risks we are facing right now. Extreme weather is one of them, but jointly with that, misinformation and disinformation are also very relevant. And at times, they are used to amplify the risk associated with climate change. So I'm going to be using, or we are using in this part of the project, a lot of AI technologies and different algorithms to differentiate the quality of the messages to understand what is the impact of information with respect to climate change. This misinformation movement is very important nowadays, and you will be surprised that this is a priority for the United Nations, to reduce the misinformation related to climate. And why? Because as I'm going to show you, these misinformation waves occur particularly, or they are very common, when there is a huge drastic event. This is we have an example from a huge flood in Spain, the Dana. It happened about 1 year ago. In 2 days, they are going to have the first year anniversary, in which 200 people have died. And there was a clear example of lack of information on one hand and misinformation on another. So we collected lots of social media data. We collected a data set on nearly 300,000 tweets that were related to this event, Dana, and that contained the words Dana, rains, precipitation, and so on and so forth during this period of time, 18th of October until the 2nd of April of this year. And what did we learn? All this information that is occurring with respect to the Dana and has circulated on the media, did it generate any resilience? Not at all, unfortunately. Very few conversations talk about the real nature of the Dana, or the flood, which was related to climate change. Climate change was only present in some conversations that occurred at the beginning. After that, whatever is up on the social media is related with political guilt and so on and so forth. So there is a missing opportunity there to create real resilience with respect to this disclosure of information. And there is a huge presence of misinformation, particularly during the extreme event per se, which complicates things in terms of rescues, in terms of activities related to the police, in terms of generating social resilience. This is only a small, as you see in the red, we have clearly identified what were fake news. But I have to advise that this is a very conservative representation of fake news. Why? Because the real percentage is much higher. And it is very difficult to identify at times fake news because they are becoming very sophisticated, very, very sophisticated. So we are using AI for that, actually, to clean up our data set and hopefully to identify those that are fake. So, but it's complex, and we have clear research hypothesis because fake news is spread much faster than regular and other type of news. They are emotionally charged. They are also using, or they are provided by marketers, so they use certain spreading technologies on the internet, and they are very powerful overall. This is just a summary of how many retweets have a fake news with respect to a message which is real. And what we find is that usually fake news travel twice as much as regular news. We had a lot of information that I'm not going to deal with now, but all I can tell you is that after we clean this data, we eliminate the fake news. Certainly we have observed that in the particular day of the Dana, we have observed a huge decrease in sentiment, and this decrease in sentiment is much more relevant precisely at the time of the day in which precipitation were the highest. So there is a clear correlation between what people were telling and were seeing, were observing, and how the outside conditions were. In sum, I am a strong believer that, well, AI is not here to save us, but it's going to help us to better model climate impacts and extreme events in particular. And it's going to be extremely helpful through computational methods for numerical data. We will be able to better assess structural changes. We will be able to better test heterogeneity and so on and so forth. But also on text data, because we're going to be able to clean up our data better. We're going to be able to identify the quality of information and so on and so forth. So in sum, I believe that AI can be extremely helpful in order to understand climate change impacts. And that's what I want to say. Thank you.
And to all our speakers for their valuable insights into how AI can help us adapt and prepare for a changing climate. Before we break out for lunch, please join me in thanking all of our speakers today, Dr. Parag Khanna, Professor Maria, and Dr. Lucas Chopra, for their fascinating insights.